Ever wonder why those massive steel beams on construction sites are shaped like an eye instead of a solid block? Or why a spinning wheel inside an engine matters? The answer is the moment of inertia, a key engineering concept that explains why things resist bending, twisting, or spinning. It's all about how mass is arranged, not just how much there is. This principle shapes everything from skyscrapers to smartphones, making structures strong and efficient. Let's dive in and see how this rotational laziness is the secret behind the world's strongest designs. Moment of inertia is an object's resistance to being spun. Think of it as how stubborn something is when you try to rotate it. Just like mass resists changes in straight-line motion, moment of inertia resists changes in rotational motion. In other words, it's often called rotational inertia. The higher the moment of inertia, the harder it is to get something spinning, or to stop it once it's spinning. It's not just about how heavy something is, but also about where that weight is placed relative to the axis of rotation. The farther the mass is from the axis, the more it resists spinning. For example, hold a baseball bat by the handle and swing. It's easy because most of the mass is close to your hands. But if you grip it by the barrel and try to swing, it suddenly feels much heavier and harder to move. That's because the mass is now farther from your hands, increasing the moment of inertia. That's moment of inertia in action, changing how easy or hard it is to rotate something just by shifting the mass. Figure skaters use this principle to their advantage. When they pull their arms in, they reduce their moment of inertia, allowing them to spin much faster with the same effort. The farther mass is from the axis, the harder it is to spin or stop spinning. That's why a merry-go-round is easier to spin when everyone sits close to the center. Engineers use this principle constantly, designing parts to either resist or allow rotation as needed, whether it's in cars, machines, or even spacecraft. Moment of inertia is the rotational equivalent of mass in linear motion, absolutely crucial for predicting how things move, spin, and stop in the real world. The formula for moment of inertia is simple: I = mx r2. The farther mass is from the center, the more it resists rotation. For beams, height matters even more. Double the height, and you get 8 times the bending resistance. That's why floor joists stand tall, not flat. For shafts, increasing the radius boosts resistance to twisting dramatically. Engineers exploit this by shaping parts to put material far from the center, gaining strength without extra weight. Stand a ruler on its edge. It's much stiffer than when it's flat. That's moment of inertia at work. The I-beam's genius is putting most of its steel in the top and bottom, maximizing strength with minimal material. The concept of moment of inertia is crucial in engineering and physics, as it determines how much an object resists changes in its motion. A high moment of inertia means an object strongly resists both spinning and bending, making it harder to start or stop its movement. This property is especially important in large machines and structural components, where stability and resistance to deformation are essential for safety and performance. Take the I-beam, for example. Its flanges are positioned far from the center, which dramatically increases its stiffness without adding unnecessary weight. This clever design allows the beam to support heavy loads efficiently, making it a staple in construction and civil engineering projects. The web, the vertical section connecting the flanges, keeps them apart and resists shear forces. By using less steel than a solid beam, the I-beam achieves strength and efficiency, optimizing material use while maintaining structural integrity. In engines, flywheels take advantage of a high moment of inertia to smooth out power delivery. They store energy during each piston stroke and release it evenly, ensuring the engine runs smoothly and efficiently, reducing vibrations and wear. In contrast, robotics and aerospace applications often require a low moment of inertia. Lightweight arms and components, positioned close to the pivot point, allow for rapid, precise movements. This enables robots to operate quickly, and aircraft to respond instantly to control inputs. Airplane control surfaces, like ailerons and elevators, are engineered to be as light and compact as possible. This design ensures they can move instantly, providing pilots with precise control and enhancing the aircraft's maneuverability and safety. Whether the goal is to resist or enable motion, mastering the moment of inertia is essential in mechanical design. Engineers carefully balance these properties to achieve the desired performance in every application. Ultimately, it's all about strategically placing material where it matters most, maximizing strength, minimizing weight, and ensuring optimal performance in every engineered structure. Take a close look at a crane's boom. Notice how it's built as a lattice, not just a solid bar of metal. This isn't just for looks, it's a clever engineering choice. The lattice design uses a network of interconnected metal pieces, forming a strong yet lightweight structure that can lift massive loads high into the air. By concentrating material along the edges, engineers maximize stiffness while keeping weight to a minimum. This approach allows structures to resist bending and flexing, making them both efficient and durable. Car suspension arms follow the same principle. They're often hollow or ribbed, designed to have a high moment of inertia exactly where it matters most. This keeps the wheels perfectly aligned, ensuring sharp handling and a smooth ride, even on rough roads. Drive shafts, too, are made as hollow tubes instead of solid rods. This clever design gives them nearly the same strength as a solid piece, but with much less weight, improving vehicle efficiency and performance. In buildings, columns are often wide I-beams or hollow tubes. These shapes are chosen to resist buckling from every direction, maximizing the moment of inertia and keeping structures standing tall and safe. Every structural shape you see is the result of careful balancing. Strength, weight, and cost are all considered. Engineers select the best geometry for each application, ensuring safety and efficiency. Today, engineers use advanced computer models and simulations to optimize these designs even further, squeezing out every bit of performance and reliability from each component. The result of all this innovation? Safer, lighter, and more efficient structures are everywhere you look, from the bridges you cross, to the cars you drive, to the skyscrapers that shape our cities. Ultimately, it's all about mastering the physics of shape, using science and creativity to build a better, stronger world. Moment of inertia is the hidden force behind strong, efficient engineering. It's not just about weight, but where that weight is placed. From I-beams to flywheels, bicycle frames to wind turbine blades, this principle shapes our world. Next time you see a bridge, crane, or even a screwdriver, notice the clever use of shape. These designs aren't accidental. They're the result of mastering rotational physics. Moment of inertia, the unsung hero making our world stronger, safer, and smarter.